Hello?
Okay. Pay attention not to put your finger
Okay.
out of it. You go in front, you go back. Sì, grazie. I'm gonna tell you when we are 5 minutes away, 2 minutes away, then I'm gonna jump on you.
Okay, very good. So, welcome to the second session of the theory afternoon of the workshop. Our first speaker is Nicolas Bernàl, and he's going to tell us about spin-to-port dark matter. Nicolas, please.
Thank you very much. So, yes, I will talk about this spin-to dark matter. So it's based in this work made in collaboration with Ian Mambrini, Keith Olive, Marco Peloso, and two great students, Maïra Dutra and Matthias Pierre. So I'm Nicolas Bernàl, I'm from University. It works? Okay, yes. Antonio Nariño in Bogotá, Colombia. So, well, we have talked a lot about dark matter, and in particular about WIMP dark matter. So just two comments on WIMP dark matter. Okay, the idea is that we have this dark matter which interacts kind of strongly with the standard model, meaning that dark matter reaches thermal equilibrium, so chemical equilibrium with the standard model. So, and at some point, right, so this is, it works? Okay, so the idea is that dark matter in the early universe is in chemical equilibrium with the standard model. So it follows the equilibrium density, and at some point the interaction rates are not strong enough. And because of the expansion of the universe, dark matter goes out of equilibrium and undergoes this freeze out. However, that's not the only possibility. As for instance, Andre was telling us about, we can also have FIMP dark matter, where the idea is that you have to solve basically the same Boltzmann equation. The main difference is that here the interaction rates are super small, and in particular, they're small enough that they don't guarantee that dark matter enters into chemical equilibrium with the standard model. Yeah, I know. But just to see if it works or not. Okay. So in the case of FIMP dark matter, you have something like this. So the idea is that when you assume that dark matter in the early universe is, the dark sector is kind of depleted. So you are starting, you create the dark matter out of standard model very slowly, and at some point you reach you have like the freezing, so reaching the measured dark matter relic abundance. So a couple of extra words on FIMP. So there are basically two kinds of FIMP. So one is the infrared FIMP, so where these very small interaction rates are due to renormalizable operators with a very small coupling. So reaction rates are very small because you have a very small coupling, so the order, say, 10 to the minus 10 or so. So these very small couplings are, as you can agree, they're unnaturally small, but at least in some modes they could be technically natural. And if all particles, or if you want the dark matter particle, the mediator, are in the electroweak scale or something like this, the bulk of the production takes place when the temperature of the universe is of the order or the mass of the dark matter or the mediator. And one thing that depends on the initial conditions. But that's not the only possibility. We can also have very small interaction rates due, in this case, to non-renormalizable operators with a high temperature dependence. For instance, this, oops, no, yes. I think the problem is that I'm colorblind, so it's difficult to me to see the pointer. Okay, there you can see the sigma V. So what I'm just saying that this has a very high temperature dependence, so typically it's T power n over a mass scale power n plus 2. So, in this case, when this FIMP happens at the UV, so dark matter is produced, the bulk of the dark matter is produced at the highest temperature of the universe. So, for instance, heating temperature or something like this. And one thing here, we don't have very small coupling. However, the small interaction rates are due to this heavy particle, heavy mediator, if you want. And these heavy mediators are kind of natural in the sense that they naturally appear in many well-motivated extensions of the standard model. For instance, if you have like high-scale supersymmetry, or if you have granified theories, or if you have leptogenesis. So it's very natural to have very heavy particles, very heavy mediators. So, now one point about the inflaton. So typically we assume that the inflaton decays instantaneously at T reheating, and T reheating is the highest temperature of the universe. So in that plot, I'm showing the temperature as a function of the scale factor. So the idea is that at T reheating, the inflaton decays, so creating the standard model bath, and this temperature will scale like 1 over the scale factor. However, this is not always a good assumption, because actually the inflaton in particular, all the particles have to take a finite amount of time for decaying. So this instantaneous decay of the inflaton may not be a good approximation. For instance, if you take into account the time that the inflaton takes to decay, so you take the inflaton decays non-instantaneously, you will find out that the T reheating is not the maximum temperature of the universe, or it will be something like we call Tmax. And during this period of time between Tmax and T reheating, the temperature of the universe will not scale like 1 over the scale factor, but more like a power minus 3/8 or so. So during this period of the universe will be not dominated by radiation, but will be like that mixture between the inflaton, so non-relativistic particles, and radiation. And now the Hubble expansion rates, when the universe is radiation dominated, scale as we know was like T squared. However, between Tmax and T reheating, the Hubble expansion rate will scale like T4, right? And I'm making all this emphasis because particularly in UV freezing, when the bulk of the dark matter is produced at the highest temperature of the universe, so making this difference between Tmax and T reheating will be a very important thing to take into account. Okay, so this is basically exactly the same slide that I showed you before. So I would just to emphasize on the case where we have UV freezing and where we can parameterize our cross-section, okay, like T power n over, if you want, a mass scale and plus 2, so where we have a very high temperature dependence. I told you the bulk of the dark matter is produced at the highest temperature of the universe. That could be either T reheating or Tmax. For instance, if n, so the cross-section scale like T power less than 6, the bulk of dark matter production happens at T reheating. However, if the dependence is even higher, if it's n is 6 or higher, the bulk of the dark matter production will take place at Tmax. So now the idea is to give like a particular example where this can happen. And this will be, surprise, surprise, spin-2 portal dark matter. So at this point, I will restart the presentation. So I'm Nicolas Bernàl from blah, blah, blah. So the model is very simple, right? So the idea is we have the standard model with a dark matter candidate and a mediator, basta. So standard model plus the graviton. Of course, we cannot get rid of the graviton. I can see this thing. Okay, the graviton H mu nu plus a dark matter particle X and a mediator, which will be H mu nu with this hat, this tilde. So it's a simplified model. So we have one particle responsible for dark matter and one mediator. So for dark matter, we'll take into account like spider spin 1, 0, or 1/2. For the plots I will show you, we'll focus on scalar dark matter. And the only thing is that we'll take the mediator to be spin 2, a massive spin 2. So the Lagrange is very simple. So we have basically no choice. So we have, I can see this guy. Okay, the standard model and the Lagrange part corresponding to dark matter. Of course, we have the graviton, so we have to take into account the Einstein-Hilbert term for graviton. But we also have this massive spin 2, so we'll have to take an equivalent of the Einstein-Hilbert Lagrangian for kinetic term of the massive spin 2. This massive spin 2, of course, has a mass term, and the only possibility is to take this Fierce-Pauli, because it's the only possibility which is Gauss-free. And also we have to add interaction terms between the mediator and the standard model. So for instance, we take the graviton, we have no choice, we have to take the interaction between graviton and the energy momentum tensor, so T mu nu for both the standard model and the dark matter X, which is of course mass Planck mass suppressed. And we also have to take the last piece of the Lagrangian, will be correspond to the interaction of the massive spin 2. So again, this spin 2 has to couple with the energy momentum tensor, and will be now inversely suppressed by this new scale lambda, right? So I'm showing you here just the stress and the expression of the stress energy tensors for 3 spins. So these so 0, 1/2, and 1 correspond to the spin. So spin 0, spin 1/2, and spin 1. So the theory, as I told you, is super simple. We have one dark matter candidate and one mediator. So we have 4 free parameters, which will be basically the dark matter mass, mx. mh tilde will be the mass of the mediator of the spin 2, and 2 couplings. So coupling of the mediator with the dark matter, and coupling of the mediator with the standard model, right? And they will be suppressed by this scale, heavy scale lambda. So the model is super simple. It's a simplified model with only 4 free parameters. So now what we want to do is produce the dark matter via the FIMP mechanism. So dark matter will be produced out of the standard model via standard model annihilations. Mediated by the S-channel exchange of both a graviton H and the massive spin 2 H tilde, right? So you have the diagram here. And we can find 4 regimes, and depending on the mass of the mediator. So for instance, when the mass, when the temperature of the universe is much higher than the scale of the mass of the spin 2, so our annihilation cross section will scale like T squared. However, when the mediator is very heavy with respect to the temperature of the universe, we'll have a case where the sigma V, where is it? Here. Goes like T6, and this will be super interesting because you can see that the annihilation cross section is super dependent on the temperature, so dependent to T6. And the case where the mediator is super heavy, meaning that the graviton will be the guy which will be dominant in this annihilation. So in that case, the cross section will go just like T squared. And the other case when we are very close to the resonance, meaning when the temperature of the universe is of the order of the mass of the spin 2. And then you have basically this expression. So here I'm showing you the rate, so annihilation rate. So if you want, it's the cross section times n squared, where n is just the dark matter number density, as a function of the inverse on the temperature. So the mass of the spin 2 over temperature. And here you can see the 4 regimes. So for high temperature, you have the light mediator regime. Then you have this bump corresponding to the resonance. Then you have a regime where you have the heavy mediator, and then when the mediator is super heavy, the interaction is mediated by the graviton. So you have these 4 regimes. And in particular, I want to focus on these 2, so when the mediator is heavy, and in the case of the resonance, because in these 2 cases, the impact on T reheating will be super important. Okay, so here I'm showing you a plot of T reheating as a function of the mass of the spin 2, right? So, and the lines I will show you correspond to the values of T reheating needed in order to reproduce the observed dark matter abundance via this FIMP mechanism. So what I have to do is to solve this set of 3 Boltzmann equations. The first one corresponds to the evolution of the dark matter number density, and the second one corresponds to the evolution of the radiation energy density, and the third is the evolution of the inflaton energy density. So I have to keep track of both these 2 energy density, meaning the energy density of radiation and the inflaton, because they will give me the evolution of the Hubble expansion rate, right? The Hubble expansion rate between, as I told you, between T max and T reheating will not be, 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 will not will not scale like t squared, but more like t4. So we have to keep track of the evolution of the Hubble expansion rate, because it's an important fundamental ingredient in the evolution, in the solution of the dark matter number density, right? So here I'm showing you the heating temperature that I need in order to reproduce the dark matter Ehrlich abundance. So first, when the mediator is super heavy, so that means that that heavy that will kind of decouple, so the annihilation rate will be mediated by the graviton exchange. So that happens when the temperature of the mediator is super heavy with respect, the mass of the mediator is super heavy with respect of Tmax. So we have a high heating temperature, which is basically independent on the mass of the spin 2, because basically the spin 2 is playing no role here. Oh, okay, thanks. If I'm started decreasing the mass of the mediator will be the one, so its contribution will dominate over the graviton. So we'll have this mediator here, this behavior here. So we have a new particle entering into the game that is mediating the dark matter production. So that means that we're increasing the cross-section, so we can decrease the reheating temperature. One thing that I forgot to tell you guys is that I'm showing you here these plots for two masses. The solid line corresponds to a super heavy dark matter of 10 to the 10 GeVs, and the dot line corresponds to a 1 GeV dark matter particle. You will see that this is kind of independent, so there's only a logarithmic dependence on the dark matter mass. So that means that these two lines will not be the same, but will be kind of similar, even if they are like 10 orders of magnitude of difference. And these dotted lines, the first one corresponds to to T reheating equal to the mass of the mediator, and the second one is T max equal to the mass of the mediator. And we are assuming that T max is 100 times T reheating, and these couplings, right? So like if you want couplings of the order of 1 with a scale of 10 to the 16 GeVs or so. Okay, so this last line that I showed you corresponds to the case where you have a heavy mediator. Now we start decreasing even more the mass of the spin 2 mediator. And in that case, we reach the resonance. So when we are in the resonance, we already have a huge increase of the interaction rate. That means we can go to even smaller T reheatings. So one thing that I want to tell you first is that I'm stopping this line here because this corresponds to the case where the mass of the dark matter is equal to the heating temperature, and if the mass of the dark matter of the dark matter is smaller than a T reheating, you will basically be on you cannot produce the dark matter out of the thermal bath. So that's why this solid line corresponding to 10 to the 10 GeVs stops here at a temperature of 10 to the 10 GeVs for a reheating temperature, because for smaller reheating temperature, you're basically not able to produce it out of the thermal bath. And now what happens if we keep decreasing the mass of the mediator? So you reach to the case where you have a light mediator. So when the mediator is much lighter than the reheating temperature, so in that case, basically the interaction rate is independent again of the light mediator, and that's why you get like a plateau here. So the reheating temperature is again independent on the dark matter, on the mass of the mediator. So I want to emphasize in these two cases, the case where the mediator, here is heavier, and in the resonance, because in that case, I told you before, the dependence on the cross-section is higher than T⁻⁶. That means that the bulk of the dark matter production happens between Tmax and T reheating. So here I'm showing you a plot of, if you want, it's like a kind of boost factor. So these plots will tells you the importance of Tmax with respect to the T reheating. So what's the, if you want, it's a proxy of the quantity of dark matter produced at Tmax and not at T reheating. So if you want, this is quantifying the error if you forgot this story of T reheating and you start the evolution of the universe if you want at T reheating. So here I'm showing you this plot for the 4 cases, for the case where the mediator is light, for the resonance, for the case where the mediator is heavy, and for the reheating. For the case where it's mediated by the graviton. So when you have a very light mediator, the boost factor, if you want, is order 1. So that means that the bulk of the dark matter is produced at T reheating. The same happens when the interaction is mediated by the graviton. However, when you have a heavy mediator, you can have a boost factor of order 20 or so, and when you're near the resonance, the boost factor could be even higher than, I don't know, 1,000 or something like this. Could be orders of magnitude much bigger than 1. So this plot, what is showing you, this is basically my last plot, is that in the case where you are close to a resonance, at least in this model, or when you spin to mediator is very heavy, the boost factor, meaning the quantity of dark matter produced at T reheating and not, at T max and not T reheating, could be orders of magnitude bigger than your naive estimation. So I think that was basically all that I wanted to tell you. So some conclusions. So first is basically the same one that Andre was pointing us. It's basically the nature of dark matter is still unknown. And the FIMP framework provides for a compelling alternative to the WIMP scenarios. So if you are mediated by heavy states or by non-renormalizable operators, you can have production a la FIMP, UV FIMP. And in that case, if the cross section is an annihilation cross section, has a very strong temporal dependence, in particular if it's higher than or is T6 or higher, the bulk of the dark matter production happens at T max, not at T reheating. So there are huge effects due to the non-instantaneous decay of the inflaton. So one example is what I show you is the dark matter produced via spin to portal. So in that case, the freezing dark matter production is enhanced during reheating in the case of a heavy mediator, or to its resonant production in the case of a light mediator. And its enhancement is of many orders of magnitude, so it's an effect that you definitely have to take into account. So one word about the possibility of testing these scenarios is, okay, this is super challenging because by construction, freezing is super challenging to test. And in particular, if dark matter is super heavy, however, we can have possible distortion of the power spectrum or non-Gaussianities. And okay, what we have to do is to keep looking for dark matter in different paradigms of production. Thank you very much.
Thank you, Nicolas. Questions?
Hey, Nicolas. Yeah. Do you see such an enhancement in gravitino production, which is also peaks at T reheat? I mean.
Yeah, but typical gravitino is T power 4, I think. So this enhancement you will not find it. So it's kind of tricky to find this enhancement because you need a super strong temporal dependence. So that's why we took this particular example. So here you have like the temporal dependence is very high because we have like two things. So one, because the mediator is heavy, and also because the couplings are very suppressed because it's spin 2.
Okay.
I think we have time for another quick question.
So just, I guess for the light mediator case, so there's this whole story of how the additional degrees of freedom of the massive spins to decouple from the rest that we'll have thought about in applications to modifications of gravity and so on. So in your case, did you take into account those and this Weinstein mechanism? How? So you have a massive spin 2 with 5 degrees of freedom, right? But when it's very light, let's say massless, it should somehow reduce to 2 degrees of freedom.
Yeah,
and
okay.
That story is a bit complicated.
Yeah.
But so I'm wondering if
when I say light, it means light with respect to T reheating, but it's still 10 to the 10.
No, okay, it's produced relativistically, right?
Yeah.
So I think that's what light means. So it's light compared to the scales relevant at the temperature at those times, right? So
right.
It seems to me that one should think about that story. Okay, I'm not totally sure, but I'm asking if you...
No, but I don't think, okay, we can discuss that. I'm not sure that's an issue. I don't see why it could be. Because anyway, it's super, super heavy. It's always relativistic, so.
Is what?
It's always relativistic in our case.
It's non-relativist? No,
no.
You have cases where the temperature was large compared to the mass, so.
I'm not sure.
Okay. So I think this is a good moment to thank again Nicolas. So we go to our next speaker. Daniel Lopez-Fogliani.
Hola. Okay.
Very good. So.
Bien.
Okay, so Daniel is going to talk us about the phenomenology of the µνSSM. So Daniel, please.
Okay, first of all, thank you very much for the invitation to this fantastic meeting and to bring together all the Latin American community. This is fantastic. Okay, this is the title of my talk. I'm going to talk about the phenomenology of this model that is a supersymmetric model that breaks a parity. I am going to very brief talk about display vertex and other signals in LHC, but that is the main topic of my talk. My talk is going to be concentrated in signals in gamma ray telescopes of dark matter. Let me say that, okay, it's still supersymmetry life. There are a lot of constraints on air parity conserving models, and in these days, it starts to be more and more constraints on air parity models. And I am going to talk about this kind of models, and it is true that it starts to be on these models, and let me talk a bit about this. But are less explored than the air parity conserving model that are kind of older, And then, in particular, I am going to talk about this superpotential. The idea is very simple. It's to take the standard model to make the supersymmetrization, but it's starting from the beginning with right-handed neutrino, because you know that you need to reproduce the neutrino physics, and the idea is to construct the simple model as possible, including right-handed neutrinos in the game. And then when you do that, and also since you want the simple model, you don't want a mu problem there, you want to make it as simple as possible, all the only scale is going to be terms, is the only scale you have. And then with this idea, this is the superpotential, the simple one, that is in principle going to reproduce the whole phenomenology. Then you have only dimensionless parameters in the superpotential. You are raking air parity because you want to generate the Majorana masses and also the mu term. And you want to have this Shukawa for the neutrinos. And then you want this. And also the mu term that is coming from here. You need to break air parity. There is not another possibility. Then you are going to generate effective mu terms, effective Majorana masses, effective Tiran masses. You are going to have a background expectation value for the fields. And now also for the left-handed S neutrinos, also develop a background expectation value. This is a very simple idea, but the consequence is dramatic. You are raking air parity, you are losing the LSP as a dark matter candidate. You don't have this as a dark matter candidate anymore. All the particles with the same charge are mixing together. You are mixing neutralinos with neutrinos, charginos with Higgsinos. The Higgses now are a lot of them. You need to include in the neutral Higgses the S neutrinos right-handed, also the neutrino left-handed. All is mixing there together. Of course, you cannot break air parity as you wish, and I have to talk about this in a few minutes. And also, well, the charge Higgs are there, no? But for that sector is the same. The only difference is that S leptons are also they are mixing with the charge Higgs. Everything mixed together. But okay, you cannot mix this as you want because you are motivated by the neutrino physics. Then the Chicago of the neutrino must be the one to reproduce neutrino property in a correct way. And the only scale you have is the Susy-Breaker scale, that is the electroweak TV Susy scale. And for that reason, at the end, you have a seesaw at the electroweak scale, which implies that the Chicago of the neutrino is of order 10 to the minus 6. And this is a very number because it's the number that is going to open the possibility of displaced vertex in the LHC. Exactly with that number, you have a displaced vertex. I want to talk a bit about this in a few minutes. That are possible to be seen detected in the LHC. Then this is more or less the idea. This is the usual thing in an air parity conserving model. You have the neutrino, but now you are mixing the neutrino with the neutrinos, and you are giving mass for the neutrinos. Okay, this is the brief introduction to the model. One important thing there is to know how to obtain the correct neutrino physics. Here you can obtain everything. You can obtain the mixing, the masses, the mass difference that are known. And there is a very particular feature of this model that even if you put diagonal thing, you put everything diagonal, and at the end you obtain a matrix for the neutrino that is mixing. This is because remember that the matrix is huge, and then when you mix the neutrinos with the Vinos, the Winos, the Higgsinos, and the right-handed neutrinos, everything mixed together, and you are going to obtain exactly what you see, that is, the neutrino like to mix together. This is one nice feature. At the end, you obtain that the neutrinos, as a prediction, you want that they are going to like mix together. But at the end, the mass matrix will be in a very simple way, simply in this way. This is not exact formula, but the formula that is very easy to remember. Here you have a seesaw that is only with an effective Majorana mass. You can think that is the Higgsiano mass. You can think that the Wino is really this here, but this goes only with the left-handed neutrinos, and you have an effective Majorana mass to cover the neutrinos. This is not the exact mass matrix for the neutrinos, but if you think on this, you are going to get more or less correct result. And you are seeing this, no? Chicago's are diagonal. Here you have used only one value for the Majorana mass, and you are obtaining a mass matrix that is mixing everything together. That is, that you could obtain with diagonal Chicago's the angles we know that are measured. Okay, this is not the main motivation for my talk. My talk is about dark matter, but let me say a few words about what happened with the particle that we were expecting to be dark matter, no? Because in principle in our head, in air parity conserving model, the neutrino is the dark matter candidate. Then what happened here to the neutrino? Well, the neutrino is going to decay because everything decays to standard model particles. And well, this is one of the analyses. There are a lot of in the literature. This is one that we have carried a few months ago. And in particular, is a creation of neutrinos, and the neutrino then decay to neutrino, and the neutrino is given a place vertex. Okay, then sorry, in this case it's a prompt. This is a prompt decay. In this case, it's a prompt decay, but it's giving a signal of 3 leptons, and this is a nice signature that already you can put an exclusion limit on the parameter space. One is the expected, and the other one is the one that you can put these constraints on the model with 100 method to 1, but still I am not showing the plot. Still with the what we have now, you already can put some constraints, and also you want there is an excess that you can believe it or not on that excess, and you could also reproduce it, but you will know what happened with the excess in LAC. They are there, but tomorrow they are not anymore. But the important thing is that it's reachable in these days. Okay, it's this kind of prompt decay. It is a prompt decay. In these days, we can put constraints on the model or to see it if we are too lucky. No. The other thing I want to show you is this is a display vertex. The idea is very similar to the one previous, but now is the neutrino, the one that is directly decaying because it's LSP, and is decaying in a way that is a display vertex. And again, it's possible to put a constraint on all what is above these lines. Here is the explanation, but I don't want to enter a lot of details. But the important thing is that, again, you can put constraint today. This is 20 method bar, is what the people already have analyzed. Then, again, in this case, with display vertex, that is more complicated analysis. The analysis is very complicated. And in this case, is the neutrino. The LSP, the neutrino left, that in principle was a candidate also in air parity conserving model, but were ruled out soon, okay? But in this case, it's giving a signal because it's decay. In principle, not ruled out, but you can explore a region of the parameter spiral list in a closed future. Okay, what I want to talk about is, okay, well, we lost neutralino, the LSP, as the dark matter. We want to have a dark matter candidate, and the first possibility is to take the one that is there, because inevitably is there is the gravitino. Then if you took the gravitino as your dark matter candidate, we have done the analysis a long time, and this is giving a signal. The simple signal is that the gravitino decays to neutrino and a photon. Okay, and in principle you can observe that, and these papers are quite old, and Fermi already put some constraints on this. Then we analyze also the three body decays of in this case in this model, and again put constraints on that. But now what I want to show is the idea of okay, say okay, but let's include the axino. Okay, in principle, the axino you need to include. You can include it or not, but if you include the axino in the game, the idea is to why not include it together? Why not to include the axino and the gravitino at the same time? Because this one is protected by two things. It's protected by the Planck scale and the fact that the air parity is broken, but not a lot. And the other one is protected by the by the symmetry, you know, where this axino appears. So then, in principle, you can obtain both of them at the same time. Of course, one is going to decay to the other one, and you need to compute the time, and which is going to be the signal. The signal is going to be similar to the one I was discussing before. Is the one going to photons. And again, you can use experiment like Fermi. In this case, we were using e-astrogram that we don't know if it's going to be built or not, but since that experiment was think with a new technology, in principle we could use it as a test. How possible is to have this kind of signals coming to the two candidate for dark matter together. The dark matter is a composition of gravitino and axino. Okay, then the idea is that this is what you are going to observe, is the photon, and it's important here that the parity is broken, but it's broken by the Chokawa of the neutrino. And at the end, this matrix that is here is not whatever you want, it's very small, it's order 10 to the minus this square is 10 to the minus 12 to 10 to the minus 16, something of that order. Depends on the parameter space where you are looking for, but in principle is something of that order. And then you can have this combined signal. Of course, you need to have the correct relativity, and you cannot be excluded. The axino and the gravitino must decay to photon, but not too much. No? There are two possibilities here. One is that the axino is the LSP and the gravitino is the next LSP. The gravitino is decaying to axion and axino, and the axino is the one that is decaying only to photon in this case. But the gravitino also goes 5 minutes. No, really. Okay. Okay, I have 5 minutes, but the idea is that the gravitino also is giving the signal to photons, but you need to be careful with the decay, the time of decay of the gravitino, because it mainly going to axion-axino, no? But if you put the constraints, this line is the one that is satisfying the correct relative density, and here you go in this direction. This is the different fraction of the LSP, which fraction of the dark matter has. Then, again with the axino LSP, this is the lifetime, and well, these curves depends on which mixing between the photon, the photino and neutrino you are using, but these are the reasonable values, okay? This is go to square. Remember that is where you need square of this. This is this mathematic here, and is in these lines. And this was the projected curve for E astrogram. But okay, we don't know what is going to happen with the astrogram, but in principle we are using this in such a way to see that in principle there is a region that we can reach here. This is excluded, it's also excluded because of dark radiation. No? Remember that in this case the gravitino is going to axino and axion. No? Okay, then in this analysis here, I am using the Navarro, Frege, and White, and then in this plot, this is the mass of the axino, this is the mass of the gravitino, and in black points, they are the ones that are already excluded, okay? Green and blue are the ones that in principle could reach an experiment similar to E astrogram, and the ones in orange are the ones that is impossible to be reached. Observe where you are going to have a double signal, that is a signal for the gravitino and for the axino, because green and blue are the ones that in principle could be seen by an experiment like this one. And in this case, okay, you cannot see a lot, but there is a small region of the parameter space where you can see a double smoking gun, that is a signal coming from the gravitino and a signal coming from the axino. Of course, there are a lot of uncertainty here. One possibility is to change to the INIAC file, and then the result is a bit different, but not a lot. Another possibility is to change the experiment to a one that is more sensitive. That is to increase the sensitivity, and then you do that, again, you open more regions that in principle are possible. This uncertainty is, in principle, we don't know exactly which experiment we want to be constructed, no? But the interesting thing is that it's something that is possible to be seen in a computer. This is, but I don't have time to discuss it, but it's very similar in the case where the gravitino is the LSP and the axino is the next LSP. Very similar results, and then let me finish. 2 minutes, perfect. I am on time. And let me say that what we are analyzing here is multi-component matter. We took the gravitino in this case, in a model that is very well activated, is a supersymmetric model with air parity broken, and the parameter that controls the air parity breaking is the Chicago the neutrino. Then that is what relates the neutrino sector with the neutrino sector, and is what is allowing us to make this kind of predictions. Okay, there are constraints in these days. There is the possibility to build some kind of experiment that could detect this kind of signals, and there is a region where you can see a double smoking gun that is very interesting, because you are seeing the signal of the two of them. Of course, is not a huge region of parameter space, but it depends on a lot of uncertainties, and this could improve on time if the experiments improve. And with this, I finish.
Thank you, Daniel. Questions? So let me ask you one thing. So in the moment in which you give up with R parity, you have a whole bunch of operators that you can write down in the superpotential, right? And here you are specifying just a few. Yeah. So do you have, let's say, a new motivation, for example, to avoid baryon parity violation?
Well, the one that violates baryon number is not a problem really, because once you set it to 0, is 0. The other one is true that are going to be generated, inevitable. Yeah. No, at the end you are thinking that the one that is controlling, or the bigger one, is the one of the Chicago the neutrino. But in principle, you are going to have the other term. LE.
Yeah, is going to be there. I'm wondering if your choice is relatively stable.
It's stable. No, that's for sure, because all the others are going to run, but or generated by loops, but controlled by Chicago neutrino, because once you set it to 0, air parity restore it.
Okay.
And then it's completely under control.
Okay. Thanks. More questions?
Just, I think you went a bit quick at the end. So could you say again, what are the prospects of observing the line or double line?
Yes, well, we must be very lucky, to observe the double line. But in principle, there is a very small region of the parameter space where we have fixed this. This is the scale of the breaking, for the axino scale, the action scale. And here is a very small region for this mass of the gravitino and this mass of the axino, where in principle you are seeing a signal from both particles. So for this mass of the gravitino and the mass of the axino also, you are seeing a double smoking gun.
And this, okay, let's say you're lucky and you're in that region of parameter space, then you're saying this is observable in some experiments. So is the rate large enough that you will...
We suppose that the sensitivity of E astrogam. This is work in collaboration with Germán Gómez Vargas. He was part of the collaboration. And in principle, we are assuming that is that sensitivity, the one that E astrogam could have. That is what we assume.
But okay, at least for gravitino, so you don't have so much freedom in the couplings, right?
No.
So I guess it either works for this point in parameter space that you have a large enough rate.
Okay, sorry. Yes, I understand now the question. Sorry. Here is the range for the mixing we are using that you cannot see, but it's 10 to the minus 8 or something like that. I also cannot see it. I don't. But it's a very specific mixing. It's the biggest one in this case. But okay, they are with that parameters. With that mixing, it's possible to fulfill neutrino physics. But it's true that you need this photino-neutrino mixing QE as big as possible.
Hi, I was wondering how sensitive this is to the kind of the assumed profile or the slope, inner slope of the profile. I'm particularly concerned about the fact that in the Milky Way, it's not an NFW, when you put baryons, the dark matter contracts, and the slope is not -1 anymore. Do you have a sense of how sensitive this is?
It depends quite a lot. In principle, in this figure I show, you can see where it is. That when you change from Iniasto is this one with the region, all these masses for the Axino and the Gravitino in principle are possible, but when you go to Navarro, Freck and White, you have almost nothing there. No, it's quite small. If you put more uncertainties, more you want to change the region, but this is something that we don't know. No, also we are guessing the sensitivity of the detector that in principle doesn't exist. No, we are making a lot of positions, but it's something that could be reachable in this day. This is the lesson, no? That it's something that in principle in these days, if the experiment is built and you are lucky, you could see it.
Okay, very good. So I think we can thank Daniel again. And we move to our last speaker. Our last speaker is going to be Daniel.
No? Beer?
Okay, so last speaker of the day, Daniel Camargo, dark matter and Z-prime U1X extension. So Daniel, please.
So what? Thank you for the good answer for letting me finish this last session. So far, we just had the lunch and dinner about this kind of dark matter, so now is the time for the dessert. Yeah, so what? Because most of the people know here that model building for dark matter, or all the people that are trying to do model building for dark matter are using these kind of gauge extensions and theta primes and stuff. So what is the new thing here? We will see. Here, okay. But first, let me just say some comments about this kind of gauge extensions. Okay, yeah, this talk will be based in this kind of words and with that, guys. Okay, first of all, with this kind of extensions, we know that we can address the same problem that, for example, effective set theories do, or simplified models, but we don't have that kind of ambiguity in some stuff, like, for example, that the transfer moment of the process has to be so small in order that the effective field theory works. Or, for example, the ambiguity between the gauge couplings or the two sectors, for example, the hidden sector or the Sandler-Morel sector, because sometimes when the people is doing simplified model for dark matter, they just find some free parameter space, but that free parameter space is based on some supposition that there are free parameters, but when you work with UV-complete models, that actually not like that. Perhaps two parameters are strongly correlated, and if you move one, you move the other one. So that is the cool thing here. Another stuff is, yeah, we can solve a lot of different problems, neutrino masses, dark matter, flavor problems, so on, and we just, yes, a few more stuff, like one extra symmetry. So this is so useful in that sense. Another important thing is, for example, we already know that LHC and other colliders are looking for new particles such a long time, and they didn't find anything yet. But anyways, this kind of extension has for free, for example, theta premediator. If you include a scalar sector, you have another scalar. So we have for free that kind of possible candidates just to produce or to explain that bumps. So there is another thing. One important, and for perhaps the more I like more, is that these kind of models are susceptible to confront with different experiments coming from dark matter, coming from collider searches of other particles. So we can confront all of that searches and then try to find or to rule out the model. So it's cool in that sense. And in lattice, we can just think that we know that, for example, there are a lot of models that put by hand discrete symmetries in order to make the dark matter candidate stable or that kind of stuff. So with these kind of extensions, for example, if we include a global symmetry, we can break down that global symmetry to a zeta2 or to other discrete symmetry in order to make that or dark matter candidate stable. So in this sense, gauge extension make the model more beautiful. And then, okay, just what? Well, here we bring some different scenarios in which we just take a look at the problems. In the first one, we work some knowledge knowledge symmetry group, in which the idea here is to constrain that kind of models with the last experiments, with the last constraints. For example, in this one, we will constrain these kind of models, in particular the U1, D minus U, this kind of symmetry, with the last xenon one-ton results. In this one, we confront this kind of gauge extension plus a scalar singlet with the last xenon result, last collider searches, even including the left searches, the less constraints, sorry. And one, we are making a view Bayes cell symmetry by including an extended scalar sector that is 2 Higgs Doublet model. But yeah, this seems like okay, but these guys are doing the same and just putting some extra things. They have actually a very good reason behind that is the common experiments. They will look for. They will put these scenarios like a benchmark point for the experiment. So this thing, this scenario. I mean, if we study this extension with different possibilities, with different gauge symmetry, like here, we will put in the table for the experiments the way to looking for that kind of, new particle or new excess or stuff. So for the near future, it will be very important to take in the table this kind of extensions in a deep study. So that is because we are this, and of course, as we have extra symmetries and extra scalar sectors, all the SUSY motivation behind is there. Like we have a 2 Higgs Doublet model, so the MSSM has the 2 Higgs Doublet model. So of course, that kind of SUSY one, I will not say the SUSY motivation, I guess here. So okay. When we work with complete models, with UV complete models, we have to take into account some stuff. Like, for example, if we include a new gauge symmetry, we will have for free a kinetic missing. But a lot of people, when make, for example, simplified model, they just don't include that kind of effect. So here we include this effect just to see what is the impact that this kind of new parameters can have in the phenomenology. We can include a vector-like fermions just to play the role of dark matter, or actually a chiral fermion that is like in the first world. The phenomenology will not change so much, but it's important to take into account that both kind of fermions are possible to include. And we have, of course, if we have extra scalar fields, we have an extended scalar sector. So all this stuff are strongly correlated to each other. A lot of gauge couplings, a lot of masses. If you move something here, you move the other there. That in simplified model and in field theory models, you just don't take into account. So, for example, something that is important here is that each one of that gauge extension, for example, we have different behavior. Here, for example, is the constraints coming from the last seamless and atlas searches for the heavy vector bosons, we can see here that some models are ruled out for some masses. For example, this one are almost, what is the easy one? This one. This one is this model is almost ruled out. All this parameter space for this model is ruled out of 5,000 GVs, but the others are still okay. So even if they coming from the same idea that is extending with a gauge symmetry, they can behave, of course, differently because they have different charge. So even another important thing is here that when you are looking for sigma prime bosons or heavy resonance, this kind of experiments assume narrow width approximation, and even if they share the same coupling, for example, the different charges as segments under the new gauge symmetry can make this model not into the narrow width approximation. So you can assume this one into narrow width approximation and make a standard searches, but this one can have a large width, so current standard codes and stuff will not work. So okay, here in this case we just confront this model with all the possible constraints. For example, here is the searches in monojet. Here is the trident production neutrino, and here this is how we vary the branching radio of the C prime going to leptons. So as we can expect, as the branching radio in leptons is growing, the mass of the C prime is more restricted. The same apply for the other scenarios, and in some of them we just fix this gauge coupling. But when you fix this gauge coupling, all these things can change, and we took into account that. So yeah, we can see here that this kind of model, for example, the mu minus tau behaves so quite different from the UX model, and that the same apply for the other model we will see. Okay. For example, here in this model, we confront this model with the last Xenon results, and as well with the prediction of the LHC, the incoming prediction. We can see here, I mean, in this case, we just took the worst scenario in which the gauge coupling is 1. We can just rescale the result. So when the gauge coupling is so large, the zeta prime, the will lack so much decay in leptons. So these kind of constraints are stronger mostly all the time. More or less here is starting to compete with the Xenon results. But yeah, just taking into account that scenarios is for this gauge coupling. So yeah, I mean, this scenario, for example, for a dark matter of 50 GBs, we can see here that is totally excluded. For this scenario that is with this one for 1 TeV, we can see that it's totally excluded, and totally excluded not just because of the Xenon results, it's just, as I say, for the LHC searches. And just this one with a very heavy dark matter candidate will survive in this small region. So this is something interesting. Okay, the other model, for example, this one that is coming from a gauge symmetry Venus cell plus a 2 Higgs double model, we can see here that the incoming experiment for the red detection are ruled out everything. And this red curve represents the points in the parameter space in which we can reproduce the Rayleigh abundance with standard cosmology. But if we invoke no standard cosmology, we can see here that this parameter space is starting to compete. For example, this one is not totally excluded for the Xenon n-ton, but for Darwin is still excluded as well. Apply for this scenario. This is for 1 TeV, and this is for 2 TeVs as the dark matter. So if even if we evoke non-standard cosmology, we can see that the upcoming experiments for direct detection can rule out the whole parameter space of this completed scenario. Well, as I say, we can just evoke this non-standard cosmology in order to save, in some sense, the model, but still, for example, Darwin will rule out everything as well here. But there are other scenarios for masses larger than 2 TeVs in which we can still have some, in the resonance like it's common, like Andre or Nicolas said, in the resonance, close to the resonance, we will be still okay with that common experiments. And here we can see the same. This is the direct detection. We can see here for these 2 scenarios, just this parameter space is okay, as well as here. This shaded region represents the excluded regions for direct detection and indirect detection. And this is the parameter. This is the benchmark point we was taking here for this symmetry. So we can see here that even if that kind of extension coming from the same speed of some extended scalar sector and gauge scalar extended gauge sector, the parameter space and the phenomenology can change a lot. So yeah, this is with a singlet scalar sector, and this with a doublet scalar sector. So okay, just take to home. Yeah, as I said at the beginning, this kind of extension can address a lot of problems. The upcoming experiment will take as a benchmark point this kind of extension, so it is important for us, the phenomenologists and theorists, to explore in more deeper these kind of extensions, and perhaps new mechanisms like non-standard cosmology can can in some sense save the models or make a new explanation for dark matter. So thank you.
Thank you, Daniel, for the very compact talk. We appreciate compact talks. So questions.
So in the last part, when you discussed about this entropy injection, I missed what the definition of the parameter delta was.
Pardon?
The parameter delta, which was set to 1 or to. How did you define delta? I missed that.
Delta is the dilution factor. It's a long history, but just to summarize, you evoke non-standard cosmology is like you put some scalar that prior to the Big Bang nucleogenesis, the density of that scalar will dominate the density scale, the density energy of the universe, and then they can make a latent inflation. That process will make a kind of the particles can dilute, and then we just parameterize that dilution with that factor. So that is the
Rayleigh density you would find in a standard cosmology divided by delta.
Yeah, exactly.
Okay.
So some abundant models can be saved because of this non-standard cosmology. In that sense.
There is no reason to stop at 10. It could be more, and so
exactly.
These lines could go below Darwin as well, right?
Yeah, it's true.
So on the plot of your right, why? Okay. So this funnel is because of the resonance, right?
Yep.
So why in the non-standard cosmology is moving towards higher masses?
Because of the size of the scan.
Okay.
Something else? Okay, very good. So let's thank Daniel and all our speakers again. So we reconvene in 10 minutes, 5-10 minutes, for the conversation about gender in science. Dai, questo mi consola perché io non stavo capendo
Cioè,
nulla.
poi tanto, sai, è come quando parlavo il portoghese, cioè delle parole di riferimento.
Ti svegli e poi...
Dici, va, forse allora vuol dire questo, però...
No, è complicato. Fammi prendere delle sedie. Va.
Ma quindi cosa funziona?
Chiamiamo le ragazze.